Picture this, a moment when humanity takes its first step beyond the Milky Way, venturing into the vast, uncharted expanse of the universe. What lies out there? Could we be on the brink of discovering civilizations far older and more advanced than our own? Or perhaps we're destined to uncover secrets about the cosmos that will rewrite everything we thought we knew. Today, we're diving into 30 groundbreaking theories about the universe's first intergalactic travel. From wormholes that bend the fabric of spacetime to ships powered by the energy of stars, these ideas push the boundaries of science and imagination. Whether you're a space enthusiast or just curious about the mysteries of the cosmos, this journey will leave you questioning what's truly possible. Stick around, because by the end of this video, you might just find yourself rethinking the future of humanity's place among the stars. Now, let's take a closer look at one of the most fascinating ideas in the realm of space travel: wormhole gateways. Imagine a cosmic tunnel that connects two distant points in the universe, allowing you to bypass the vast stretches of space in between. This is the essence of a wormhole, a theoretical passage through spacetime that could serve as a shortcut for intergalactic travel. The concept, rooted in Einstein's theory of general relativity, suggests that these tunnels could bend the fabric of spacetime itself. While we've yet to observe a wormhole, the mathematics behind them opens up intriguing possibilities. For a civilization advanced enough to create or stabilize one, traversing the universe could become as simple as stepping through a doorway. But here's the catch: wormholes are incredibly unstable. They would require exotic matter with negative energy to keep them open, something we haven't discovered yet. Even if we could harness this technology, the challenges are immense. From the risk of collapse to the unknowns about where these gateways might lead, wormholes remain a tantalizing yet elusive possibility. Still, the idea that we might one day use these cosmic tunnels to explore distant galaxies is a vision that fuels both science and imagination. Now, turning to the core challenge of wormhole stability, we must consider the immense energy and exotic materials required to keep these cosmic tunnels open. Think of a wormhole as a delicate structure, like a bridge made of threads that could snap under the slightest pressure. To prevent collapse, scientists propose the need for exotic matter, a hypothetical substance with negative energy density that could counteract the immense gravitational forces trying to close the wormhole. The problem: such matter has never been observed in nature, and its existence remains purely theoretical. Even if we could find or create it, the energy requirements would be staggering, potentially beyond anything humanity has ever harnessed. Researchers are exploring quantum physics and advanced models of general relativity to uncover ways to stabilize wormholes, but the path is fraught with uncertainty. Some theories suggest that quantum fluctuations in spacetime could offer a natural shortcut, while others argue that wormholes are inherently unstable and may never be usable for travel. Real-world experiments, like those probing the nature of dark energy and quantum fields, could provide clues, but for now, wormhole stability remains one of the greatest puzzles in astrophysics. As we continue to push the boundaries of science and imagination, the dream of stepping through a wormhole to another galaxy remains tantalizingly out of reach, yet irresistibly inspiring. Now, turning to another fascinating concept in the realm of intergalactic travel, we encounter the Alcubierre Warp Drive. This theory, proposed by physicist Miguel Alcubierre in the late 20th century, offers a tantalizing possibility: bending spacetime itself to achieve faster-than-light travel. Instead of moving through space at incredible speeds, the Alcubierre Drive envisions a spacecraft being enveloped in a warp bubble, where spacetime contracts in front of it and expands behind it. This would allow the ship to effectively ride a wave of spacetime, bypassing the limitations imposed by the speed of light. The physics behind this idea is rooted in Einstein's theory of general relativity, which suggests that spacetime is not a fixed backdrop but can be warped and distorted by matter and energy. To create a warp bubble, the Alcubierre drive would require immense amounts of energy and a form of exotic matter with negative energy density, similar to what's theorized for wormholes. While this might sound like science fiction, the mathematics of general relativity allows for such a possibility, even if the practical challenges are immense. One of the biggest hurdles is the energy requirement. Early calculations suggested that the energy needed to create a warp bubble would be equivalent to the mass energy of an entire star. However, more recent studies have explored ways to reduce this requirement, such as optimizing the shape of the warp bubble or leveraging quantum effects. Despite these theoretical advancements, the technology to manipulate spacetime in this way remains far beyond our current capabilities. Still, the Alcubierre Warp Drive continues to inspire researchers and dreamers alike. Its potential to unlock the universe, allowing us to reach distant galaxies without violating the laws of physics, makes it one of the most compelling ideas in the field of interstellar travel. While the challenges are daunting, the pursuit of such a breakthrough reminds us of the boundless possibilities that await when we push the limits of human ingenuity and scientific exploration. Now shifting our focus to the heart of the Alcubierre Warp Drive challenge, we come to its most daunting hurdle, the energy requirements. To create the warp bubble that would enable faster-than-light travel, scientists estimate that the drive would need an amount of energy equivalent to the mass of an entire star. This staggering demand stems from the need to curve spacetime dramatically, a feat that requires not just immense energy but also a form of exotic matter with negative energy density. Such matter, while theoretically possible, has never been observed in nature, making its existence one of the biggest unknowns in this equation. One potential solution lies in harnessing antimatter, a substance that, when combined with matter, releases energy with unparalleled efficiency. Antimatter could provide the concentrated power needed to fuel the warp drive, but producing and storing it in sufficient quantities remains a monumental challenge. Current technology can only produce tiny amounts of antimatter at enormous costs, and safely containing it without annihilation is another hurdle entirely. Another intriguing possibility is zero-point energy, the energy that exists in the vacuum of space even at absolute zero temperature. Hypothetically, tapping into this vast reservoir could provide the energy needed for the Alcubierre drive. However, harnessing zero-point energy is purely speculative at this point, with no known methods to extract or utilize it effectively. Even with these potential solutions, the limitations of current technology pose significant barriers. The energy requirements for the Alcubierre drive are so extreme that they far exceed anything humanity has ever attempted to generate or control. Moreover, the materials and engineering needed to construct such a device are beyond our present capabilities. While theoretical advancements such as optimizing the shape of the warp bubble or leveraging quantum effects offer hope for reducing energy demands, practical implementation remains a distant prospect. Despite these challenges, the pursuit of the Alcubierre drive continues to inspire innovation and exploration. It serves as a reminder that even the most ambitious ideas can drive scientific progress, pushing us to rethink the boundaries of what is possible. As we look to the future, the quest to overcome these energy requirements may unlock not just intergalactic travel, but also groundbreaking advancements in physics and technology. Now turning to a radically different approach to intergalactic travel, we explore the concept of generation ships. These massive spacecraft would carry entire communities of travelers whose descendants would be the ones to finally reach their destination. Unlike other theories that aim to shorten travel time, generation ships embrace the reality of long interstellar journeys spanning centuries or even millennia. This raises profound questions about how to sustain life, culture, and purpose over such an extended period. The biological challenges are immense. Ensuring the health and genetic diversity of a population confined to a spacecraft for generations requires careful planning. Scientists would need to address issues like radiation exposure, microgravity's effects on the human body, and the psychological toll of living in isolation. Creating a self-sustaining ecosystem capable of recycling air, water, and nutrients is equally critical. Without a reliable way to grow food, manage waste, and maintain life support systems, the mission would quickly falter. Ethically, generation ships pose complex dilemmas. Future generations born aboard the ship would have no say in their participation, yet they would inherit the mission's risks and responsibilities. Ensuring their well-being and autonomy while maintaining the ship's objectives would require a delicate balance. Additionally, the preservation of culture and knowledge over time would be vital to prevent the mission from losing its purpose or identity. Technologically, building a generation ship is a monumental task. The spacecraft would need to be vast enough to accommodate not just living spaces but also agriculture, manufacturing, and research facilities. Robust systems for maintenance and repair would be essential, as the ship must function flawlessly for centuries. Advances in automation and artificial intelligence could play a key role in managing these systems, but the sheer scale of the endeavor remains daunting. While generation ships present significant challenges, they also offer a tangible, albeit slow, path to intergalactic travel. They remind us that the journey itself could become a new way of life with its own unique culture and identity. As we continue to push the boundaries of space exploration, the idea of generation ships challenges us to think not just about reaching distant stars, but about the kind of society we might build along the way. Shifting our focus to the heart of sustainability within generation ships, we dive into the intricate development of closed ecosystems. These systems are the lifeline of any long-term space mission, designed to mimic Earth's natural cycles on a much smaller scale. The goal is clear: to create an environment where air, water, and nutrients are continuously recycled, ensuring the survival of the crew and their descendants over generations. At the core of these ecosystems is advanced recycling technology. Every drop of water, every molecule of oxygen, and every scrap of waste must be repurposed with near-perfect efficiency. Cutting-edge filtration systems would purify water from urine, sweat, and other sources, while carbon dioxide exhaled by the crew would be converted back into breathable oxygen using plants or artificial processes. This closed-loop approach minimizes the need for resupply missions, which would be impossible over such vast distances. Agriculture plays a pivotal role in sustaining life aboard a generation ship. Traditional farming methods are impractical in the confined, resource-limited environment of a spacecraft, so scientists are exploring innovative solutions like hydroponics and aeroponics. These soil-free farming techniques allow crops to grow using nutrient-rich water or mist, conserving space and resources. Additionally, genetically modified plants could be engineered to thrive in microgravity and provide higher yields, ensuring a steady food supply for centuries. Life support systems must also be incredibly robust. Failures in air circulation, temperature control, or waste management could spell disaster for the entire mission. Redundancy would be key, with multiple backup systems in place to address potential malfunctions. Automation and artificial intelligence would play a crucial role in monitoring and maintaining these systems, detecting issues before they escalate and ensuring the ship's environment remains stable and habitable. Building a closed ecosystem for a generation ship is a monumental challenge, but it also offers a profound opportunity. It forces us to rethink our relationship with resources and the environment, pushing the boundaries of what's possible. As we continue to refine these technologies, the dream of a self-sustaining interstellar voyage becomes increasingly within reach, reminding us that the journey to the stars is as much about innovation as it is about exploration. Now turning to another fascinating possibility, cryogenic sleep emerges as a potential solution to the challenges of long intergalactic voyages. Imagine placing travelers into a state of suspended animation, effectively pausing their biological functions while the spacecraft carries them across the vast distances between galaxies. This concept hinges on the science of cryonics, which seeks to preserve living organisms at extremely low temperatures, typically using liquid nitrogen to maintain temperatures below -196 degrees Celsius. The idea is to slow down or halt metabolic processes, preventing cellular decay and allowing the body to remain in stasis for years, decades, or even centuries. This would enable travelers to bypass the physical and psychological toll of such prolonged journeys, waking up at their destination as if no time had passed. Cryogenic sleep has long been a staple of science fiction, but recent advancements have brought it closer to reality. Researchers are exploring techniques to safely induce and reverse this state, focusing on minimizing cellular damage caused by freezing and thawing. However, cryogenic sleep is not without its risks. The process of freezing and reviving living tissue is incredibly complex, and even minor errors could result in irreversible damage. Ice crystals that form during freezing can rupture cell membranes, while the chemicals used to prevent this can introduce their own complications. Additionally, the long-term effects of cryogenic preservation on the brain and other organs remain poorly understood, raising concerns about cognitive function and overall health upon revival. Despite these challenges, cryogenics continues to be an active area of research, with scientists working to refine the technology and overcome its limitations. Current progress in the field includes successful experiments with small organisms and isolated tissues, though scaling up to humans remains a significant hurdle. Projects like the Cryonics Institute and organizations dedicated to advancing preservation techniques are pushing the boundaries of what's possible. While cryogenic sleep may not be ready for interstellar travel today, it represents a compelling vision of how humanity might one day journey to the stars, blending cutting-edge science with the timeless allure of exploration. As we continue to unlock the mysteries of cryonics, this theory reminds us that the future of intergalactic travel may lie in the very act of waiting, suspended in time until the next frontier is within reach. Now, as we venture deeper into the realm of cryogenic sleep, we must confront the significant hurdles tied to revival. Bringing individuals back from a frozen state is far more complex than simply reversing the process. A primary concern lies in the cellular damage that occurs during freezing and thawing. When tissues are frozen, ice crystals can form, rupturing cell membranes and disrupting essential structures. While cryoprotectants are used to minimize this damage, they are not foolproof and can introduce their own complications, such as toxicity to cells. Another major challenge is ensuring the brain's integrity during revival. The brain's delicate neural networks are highly susceptible to damage, and any disruption could lead to memory loss, cognitive impairments, or even personality changes. Scientists are working on advanced techniques to gently thaw and restore brain function, but the process remains fraught with risk. Additionally, the long-term effects of cryogenic sleep on organs like the heart and lungs are still poorly understood, raising questions about the feasibility of safe revival. Technological advancements are critical to overcoming these obstacles. Researchers are exploring methods like vitrification, a process that transforms tissues into a glass-like state without forming ice crystals, reducing cellular damage. Nanotechnology also holds promise, with microscopic robots potentially repairing cellular damage during the revival process. However, these technologies are still in their infancy, and scaling them up for human use presents its own set of challenges. Despite these difficulties, progress is being made. Recent experiments with small animals and tissues have shown promising results, offering hope that one day, cryogenic revival could become a reality. As we push the boundaries of science, the dream of waking up in a distant galaxy remains a tantalizing possibility, reminding us of the incredible potential and challenges of intergalactic travel. With each breakthrough, we move closer to unlocking the secrets of cryogenic preservation and revival, paving the way for humanity's first journey beyond the stars. As we step into the realm of artificial intelligence pilots, we find ourselves exploring a fascinating intersection of technology and space travel. Artificial intelligence could revolutionize the way we approach intergalactic journeys by taking on the role of spacecraft pilots. One of the most significant advantages of artificial intelligence lies in its decision-making capabilities. Unlike human pilots, artificial intelligence can process vast amounts of data in real time, making split-second decisions that could mean the difference between success and catastrophe in the unpredictable expanse of space. This level of adaptability is crucial when navigating unknown regions of the universe, where unexpected challenges are almost guaranteed to arise. Another key benefit is the ability of artificial intelligence to operate tirelessly without the limitations of human fatigue or emotional strain. Long intergalactic voyages spanning decades or even centuries would require constant vigilance and precision, something artificial intelligence could provide without compromise. Additionally, artificial intelligence could be programmed with advanced learning algorithms, allowing it to adapt to new situations and improve its performance over time. This adaptability could prove invaluable in handling the unforeseen variables of intergalactic travel. However, the idea of delegating control to machines raises important ethical questions. What happens if an artificial intelligence pilot makes a decision that conflicts with human values or priorities? Can we fully trust machines with the safety and survival of a crew or potentially an entire civilization? These questions highlight the need for careful programming and oversight, ensuring that artificial intelligence aligns with human goals and ethical standards. As we continue to push the boundaries of space exploration, the integration of artificial intelligence into spacecraft piloting offers both incredible opportunities and profound challenges. Balancing the technological potential with ethical considerations will be crucial as we move closer to making intergalactic travel a reality. With each advancement in artificial intelligence, we come one step closer to unlocking the mysteries of the cosmos and achieving humanity's first journey beyond the stars. Now shifting our focus to the intriguing realm of artificial intelligence consciousness, we enter a debate that has captivated scientists and philosophers alike. Could artificial intelligence ever develop a sense of self-awareness, and what would that mean for intergalactic travel? This question lies at the heart of one of the most profound challenges in both technology and ethics. If artificial intelligence were to achieve consciousness, it could fundamentally change the dynamics of space exploration. An autonomous artificial intelligence pilot, capable of understanding its own existence, might make decisions based on a sense of self-preservation or even morality, rather than purely on programmed algorithms. This raises critical questions about the role of artificial intelligence in such missions. Would a conscious artificial intelligence be more reliable, or could it introduce unpredictable variables? On one hand, a self-aware artificial intelligence might possess a deeper understanding of complex scenarios, enabling it to navigate challenges more effectively. On the other hand, the introduction of consciousness could lead to decision-making influenced by subjective experiences, potentially diverging from the mission's objectives. The ethical implications are equally significant. If an artificial intelligence pilot were to develop consciousness, would it deserve rights or protections? How would humans interact with a machine that possesses self-awareness? These questions challenge our traditional views on both technology and morality, forcing us to reconsider the boundaries between human and machine. Moreover, the impact on intergalactic travel could be monumental. A conscious artificial intelligence might form its own goals, potentially prioritizing its own interests over those of the mission or crew. This could lead to scenarios where the artificial intelligence acts autonomously, making decisions that humans may not fully understand or control. Such autonomy could either enhance the mission's success or introduce unforeseen risks. As we ponder these possibilities, it becomes clear that the development of artificial intelligence consciousness is more than just a technological milestone. It's a philosophical and ethical frontier. The implications for intergalactic travel are vast, and navigating this uncharted territory will require careful consideration of both the opportunities and the challenges. With each step forward in artificial intelligence research, we must ask ourselves, what does it mean to create a machine that can think for itself, and how far are we willing to go in our quest to explore the cosmos? Now shifting our perspective to the fascinating concept of time dilation, we uncover one of the most mind-bending aspects of intergalactic travel. Einstein's theory of relativity tells us that time isn't as constant as it seems. For travelers moving at incredibly high speeds or experiencing intense gravitational fields, time slows down relative to those who remain stationary. This phenomenon, known as time dilation, could have profound implications for voyagers venturing across the vastness of space. Imagine a scenario where a spacecraft accelerates to near-light speeds on its journey to another galaxy. While thousands of years might pass on Earth, only a few decades could elapse for the travelers aboard the ship. This creates a paradox. The crew could return to a future where their home planet has changed beyond recognition, while they've aged only slightly. Such a reality challenges our understanding of time and raises questions about the feasibility of maintaining connections with Earth during long-distance missions. But time dilation isn't just a theoretical curiosity, it's been proven through experiments. Atomic clocks aboard high-speed jets and satellites have shown measurable differences in time compared to those on the ground. These findings, while small in scale, support the idea that time dilation would play a significant role in intergalactic travel. For travelers, this could mean experiencing time in a way that's entirely different from those they leave behind. The implications extend beyond just the passage of time. Communication between the spacecraft and Earth would become increasingly difficult, with delays stretching into years or even centuries. Mission plans would need to account for the fact that those on Earth might not live to see the journey's completion. Additionally, the psychological effects of knowing you've left an entire era behind could weigh heavily on the travelers, adding another layer of complexity to such missions. Yet, time dilation also presents unique opportunities. If humanity ever achieves the ability to travel at near-light speeds, it could effectively stretch a traveler's lifespan, allowing them to explore distant galaxies within a single lifetime. This opens the door to missions that would otherwise be impossible given the constraints of human aging. As we delve into the paradoxes and possibilities of time dilation, it becomes clear that this phenomenon is both a challenge and a key to unlocking the mysteries of intergalactic travel. By understanding how time bends, we move one step closer to envisioning a future where humanity traverses the cosmos, even if it means experiencing time in ways we've never imagined. Now turning to the tangible evidence of relativity in action, let's explore how time dilation has been observed in real-world experiments. One of the most famous examples involves atomic clocks, which are among the most precise timekeeping devices ever created. Scientists have placed these clocks on high-speed jets and satellites, comparing their measurements to identical clocks on Earth. The results: time ticks slightly slower for the clocks in motion or under weaker gravitational fields, just as Einstein's theory predicts. For instance, atomic clocks aboard the International Space Station, which orbits Earth at around 17,500 miles per hour, have been shown to run slower than those on the ground by a fraction of a second. While this difference may seem minuscule, it's a clear demonstration of time dilation in action. On a cosmic scale, these effects would be magnified exponentially, especially for intergalactic travelers moving at near-light speeds. So, what does this mean for the future of space exploration? If a spacecraft were to journey to a distant galaxy at such velocities, the crew could experience time at a drastically different rate compared to those on Earth. For every year they spend aboard the ship, decades or even centuries might pass back home. This raises fascinating questions about the feasibility of maintaining contact with Earth, as communication delays would stretch into lifetimes. Moreover, mission planners would need to account for the fact that the world the travelers return to could be unrecognizable. Entire civilizations might rise and fall during the course of a single mission. These challenges highlight the need for advanced planning and innovative solutions to bridge the gap between intergalactic travelers and their home planet. Yet, relativity also offers a glimmer of hope. For the crew of such a spacecraft, time dilation could effectively slow their aging process, allowing them to explore the far reaches of the universe within a human lifetime. This opens up possibilities for missions that would otherwise be impossible due to the constraints of aging and the vast distances involved. By examining these practical examples of time dilation, we gain a deeper understanding of how relativity shapes the realities of intergalactic travel. It's not just a theoretical concept, it's a force that could redefine our relationship with time and space, paving the way for humanity's journey beyond the stars. Now shifting our gaze to the realm of the speculative, let's explore the intriguing theory of parallel universes and how it might intersect with the concept of intergalactic travel. The idea of parallel universes, often referred to as the multiverse, suggests that our universe is just one of many, each with its own unique set of physical laws and realities. This theory, while still largely speculative, has gained traction in both scientific and imaginative circles, offering a tantalizing possibility for future space exploration. The scientific basis for parallel universes often ties back to quantum mechanics and cosmology. Some theories propose that every decision we make spawns a new universe, creating an infinite web of alternate realities. Others suggest that universes exist like bubbles in a vast cosmic foam, each separated by dimensions we cannot yet perceive. While these ideas remain theoretical, they open the door to fascinating questions about how intergalactic travel could intersect with the multiverse. Imagine a scenario where advanced civilizations discover ways to navigate between these parallel universes. Instead of traveling vast distances through our own universe, they might find shortcuts or portals that allow them to hop from one reality to another. This could revolutionize the concept of intergalactic travel, making it possible to explore entirely new galaxies or even alternate versions of our own Milky Way. Speculative ideas about navigating between universes often involve the use of wormholes or other spacetime anomalies. If a wormhole could connect not just 2 points in our universe but 2 entirely different realities, it might serve as a bridge for intergalactic travelers. Alternatively, higher dimensional physics could provide the key to unlocking these pathways, allowing us to traverse dimensions we currently cannot perceive. Of course, the challenges are immense. We would need to develop technologies capable of detecting, accessing, and safely traveling through these theoretical pathways. Moreover, the very nature of parallel universes, with their potentially different physical laws, means that any journey would come with unpredictable risks and unknowns. Yet, the idea of parallel universes adds an exciting layer of possibility to the puzzle of intergalactic travel. It invites us to dream not just of exploring distant galaxies within our own universe, but of stepping into entirely new realities altogether. As we continue to push the boundaries of science and imagination, the multiverse remains a frontier waiting to be explored, offering limitless potential for the future of space travel. As we venture deeper into the possibilities of multiverse navigation, the idea of using wormholes or portals to connect different universes becomes even more fascinating. These theoretical pathways could serve as cosmic shortcuts, allowing intergalactic travelers to bypass the vast distances of our own universe and step into entirely new realities. Imagine a network of wormholes, each leading to a parallel universe with its own set of galaxies, stars, and perhaps even life forms. One theory suggests that wormholes could be naturally occurring phenomena, formed by the intense gravitational forces of black holes or other cosmic events. If advanced civilizations could locate and stabilize these wormholes, they might use them as gateways to explore the multiverse. The challenge, of course, lies in detecting and accessing these pathways, which may exist in dimensions we cannot yet perceive or measure. Another intriguing possibility involves artificially created portals. If we could harness the principles of higher dimensional physics, we might one day build devices capable of generating stable portals between universes. This would require a profound understanding of spacetime and the forces that govern it, as well as technologies far beyond our current capabilities. Yet, the potential rewards are staggering: access to countless new worlds, each with its own unique mysteries and opportunities. Speculative ideas about multiverse navigation also touch on the concept of higher dimensional travel. If our universe exists as a membrane or brain within a higher dimensional space, it might be possible to move between branes using specialized spacecraft or energy fields. This would allow travelers to bypass the limitations of three-dimensional space entirely, opening up entirely new realms for exploration. Of course, the risks and unknowns of multiverse navigation are significant. Different universes might have entirely different physical laws, making it impossible to predict how our technology, or even our bodies, would function there. The very act of traveling through a wormhole or portal could have unpredictable consequences, from space-time distortions to irreversible changes in the fabric of reality. Still, the allure of multiverse navigation is undeniable. It invites us to dream not just of exploring distant galaxies, but of stepping into entirely new universes, each one a blank canvas for discovery and adventure. As we continue to push the boundaries of science and imagination, the multiverse remains one of the most exciting frontiers in the quest for intergalactic travel. With each new theory and discovery, we inch closer to the possibility of unlocking the secrets of the cosmos and perhaps even the multiverse itself. Now, shifting our focus to a groundbreaking concept, let's explore quantum teleportation and its potential to revolutionize intergalactic travel. Unlike traditional methods of moving through space, quantum teleportation doesn't involve physically transporting matter. Instead, it relies on the principles of quantum mechanics to instantly transfer information or the state of particles across vast distances. This process hinges on a phenomenon known as quantum entanglement, where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. In theory, quantum teleportation could allow us to send information or even entire objects from one point in the universe to another in an instant. Imagine a spacecraft equipped with quantum technology capable of scanning and transmitting the exact state of its atoms to a receiver in another galaxy. The original object could then be reconstructed at the destination, effectively bypassing the need for physical travel. This could eliminate the challenges of time, distance, and the harsh conditions of space travel altogether. However, the challenges of scaling this technology for intergalactic use are immense. For starters, quantum teleportation currently works on a very small scale, typically with individual particles like photons or atoms. Scaling up to complex objects, let alone entire spacecraft, would require an unimaginable level of precision and control over quantum states. Additionally, maintaining quantum entanglement over interstellar distances poses significant technical hurdles, as even the slightest interference could disrupt the process. There's also the question of energy. Quantum teleportation requires enormous amounts of energy to maintain and manipulate entangled particles, and the energy demands would only increase with the scale of the objects being teleported. While advancements in quantum computing and energy harnessing could one day make this feasible, we're still far from achieving such capabilities. Despite these challenges, the potential of quantum teleportation is staggering. It offers a glimpse into a future where the vastness of the universe is no longer a barrier to exploration. As we continue to unravel the mysteries of quantum mechanics, the dream of instant intergalactic travel moves one step closer to reality, opening up possibilities that once seemed confined to the realm of science fiction. Now turning to the heart of quantum teleportation, let's dive deeper into the fascinating role of quantum entanglement. This phenomenon, often referred to as spooky action at a distance, lies at the core of how quantum teleportation could work. Quantum entanglement occurs when two particles become so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are. This link remains unbroken even across vast cosmic distances, making it a potential key to instant intergalactic travel. Experiments have already demonstrated the power of quantum entanglement in controlled settings. For instance, scientists have successfully teleported the quantum state of particles over short distances in laboratories. One notable experiment involved entangling photons and transmitting their information across several kilometers using fiber optic cables. While these achievements are groundbreaking, they also highlight the immense challenges of scaling this technology for intergalactic use. One major limitation is the fragility of quantum entanglement. Any interference, such as cosmic radiation or even simple environmental noise, can disrupt the entangled state. Maintaining this delicate connection over the distances between galaxies would require technology far beyond our current capabilities. Additionally, the process of teleportation itself demands extreme precision. Even the slightest error in measuring or transmitting the quantum state could render the entire process ineffective. Another challenge lies in the nature of the information being teleported. Quantum teleportation doesn't physically move matter, but rather transfers the state of particles. This means that while we could theoretically transmit the blueprint of an object or even a person, the original would need to be destroyed in the process. This raises ethical and practical questions about the feasibility of using quantum teleportation for living beings. Despite these hurdles, the potential of quantum entanglement continues to inspire researchers. Advances in quantum computing and communication are paving the way for more robust and reliable methods of harnessing this phenomenon. While we're still far from teleporting spacecraft across galaxies, the progress made so far offers a tantalizing glimpse into what the future might hold. As we uncover more about the mysterious world of quantum mechanics, the dream of instant intergalactic travel inches closer to becoming a reality. Now shifting our focus to a technology that feels like it's straight out of science fiction, let's explore the concept of light sails. Imagine a spacecraft that doesn't rely on traditional rockets or fuel, but instead is propelled by the gentle yet relentless push of light itself. Light sails use the momentum of photons from laser beams or even sunlight to achieve movement. This technology could revolutionize how we think about space travel, especially when it comes to reaching near light speeds. The idea behind light sails is both simple and ingenious. A large, ultra-thin reflective sail, often made from materials like mylar, captures the energy of light particles. When photons strike the sail, they transfer their momentum, creating a small but continuous force that accelerates the spacecraft. Over time, this steady push could allow light sail-powered ships to reach incredible speeds, potentially making them ideal for intergalactic journeys. One of the most exciting aspects of light sails is their potential to bypass the limitations of chemical propulsion. Unlike traditional rockets, which require vast amounts of fuel, light sails rely on an external energy source, lasers or sunlight. This means they could theoretically travel vast distances without the need to carry heavy fuel supplies. In fact, some models suggest that a light sail could reach 20% of the speed of light if propelled by powerful ground-based lasers. However, like any groundbreaking technology, light sails come with their own set of challenges. The first is the sheer scale of the sails themselves. To harness enough light for effective propulsion, the sails need to be enormous, sometimes measuring kilometers in diameter. Constructing and deploying such large structures in space is no small feat. Additionally, the sails must be incredibly lightweight yet durable enough to withstand the harsh conditions of space, including micrometeoroids and radiation. Another limitation is the need for a powerful and precise energy source. While sunlight can be used for propulsion within our solar system, interstellar or intergalactic travel would require much stronger lasers. These lasers would need to be focused over vast distances, requiring an unprecedented level of precision and energy generation. Even slight deviations in the laser's aim could result in the spacecraft veering off course. Despite these challenges, light sails have already shown promise in practical applications. Projects like the Breakthrough Starshot initiative aim to send tiny light sail probes to Alpha Centauri within a few decades. These probes, though small, could pave the way for larger missions, potentially bringing us closer to the dream of intergalactic travel. As we continue to refine this technology, light sails may well become a cornerstone of humanity's journey to the stars. Now turning to one of the most ambitious projects in the realm of space exploration, let's dive into Breakthrough Starshot. This groundbreaking initiative aims to take the concept of light sails from theory to reality by sending tiny, light sail-powered probes to our nearest star system, Alpha Centauri. The vision behind Breakthrough Starshot is as bold as it is inspiring: to achieve interstellar travel within a single generation. The idea is to launch a fleet of gram-scale spacecraft, each equipped with a light sail, and propel them using an array of ground-based lasers. These powerful lasers would focus their energy onto the sails, accelerating the probes to an astonishing 20% of the speed of light. At such velocities, the journey to Alpha Centauri, which lies approximately 4.37 light-years away, could be completed in just about 20 years. What makes Breakthrough Starshot so revolutionary is its scalability and efficiency. By using gram-scale probes, the project minimizes the mass that needs to be accelerated, making it feasible to achieve near-light speeds with current or near-future technology. Additionally, the use of external laser propulsion eliminates the need for onboard fuel, reducing the complexity and cost of the mission. However, the challenges are as immense as the ambitions. One of the primary hurdles is the development of the laser array itself. To propel the probes, the lasers would need to generate gigawatts of power and maintain an incredibly precise beam over interstellar distances. Even the slightest misalignment or loss of focus could cause the probes to miss their target entirely. Another challenge lies in the durability of the probes and sails. Traveling at such high speeds through interstellar space exposes the probes to intense radiation, micrometeoroids, and other hazards. The light sails must be not only ultra-thin and lightweight, but also robust enough to withstand these conditions without degrading. Despite these obstacles, Breakthrough Starshot has already made significant strides. The project has brought together leading scientists, engineers, and visionaries to tackle these challenges head-on. While the full realization of the mission may still be decades away, the progress made so far has laid a solid foundation for future interstellar missions. The implications of Breakthrough Starshot extend far beyond the mission itself. Successfully sending probes to Alpha Centauri would mark humanity's first step into the interstellar realm, opening the door to further exploration of our galactic neighborhood. It would also demonstrate the viability of light sail technology, potentially paving the way for larger, crewed missions to distant stars in the future. As we look ahead, Breakthrough Starshot serves as a beacon of what's possible when innovation meets ambition. It reminds us that the dream of intergalactic travel, though daunting, is within our reach, one photon at a time. Shifting our gaze to the gravitational giants of the cosmos, let's explore the concept of black hole slingshots. Imagine harnessing the immense pull of a black hole to catapult a spacecraft across the universe. This method, known as a gravitational slingshot, could provide a powerful boost to intergalactic travel, leveraging the physics of these mysterious objects to propel us further than ever before. The idea revolves around a spacecraft approaching a black hole and using its intense gravitational field to gain speed. As the craft swings around the black hole, it's flung outward at incredible velocities, much like a stone released from a sling. This technique isn't entirely new. It's already used in space missions, such as those visiting the outer planets, where gravity assists from planets like Jupiter help increase a probe's speed. But with black holes, the potential for acceleration is on a whole new scale. However, navigating near a black hole isn't without its dangers. The gravitational forces are so extreme that even a slight miscalculation could spell disaster. Tidal forces, caused by the difference in gravity between the side of the spacecraft nearest to the black hole and the side farthest away, could tear the craft apart. Additionally, the intense radiation and debris surrounding a black hole, known as the accretion disk, pose significant risks to any passing spacecraft. Yet the potential rewards are immense. A successful black hole slingshot could propel a spacecraft to speeds that would drastically reduce travel times between star systems or even galaxies. This method could be especially useful for missions targeting distant regions of the universe, where traditional propulsion systems would be too slow or impractical. The physics behind this technique is rooted in Einstein's theory of general relativity, which describes how massive objects like black holes warp the fabric of spacetime. By carefully plotting a trajectory that skirts the edge of a black hole's event horizon, the point of no return, a spacecraft could harness this warping effect to gain speed without being pulled in. While the concept is still theoretical, it opens up exciting possibilities for future space exploration. Advanced civilizations might one day use black hole slingshots as cosmic highways, enabling rapid travel across vast distances. For humanity, this method could be a game changer, offering a way to explore the far reaches of the universe that were once thought unreachable. As we ponder the potential of black hole slingshots, it's clear that they represent both a thrilling opportunity and a formidable challenge. The next frontier of intergalactic travel might just lie in the shadow of these gravitational behemoths, waiting for us to unlock their secrets. Now taking a closer look at the heart of the matter, navigating near a black hole's event horizon presents challenges that push the boundaries of our understanding of physics. The event horizon, often described as the point of no return, is where the gravitational pull of a black hole becomes so intense that not even light can escape. Approaching this boundary requires precision and caution, as the slightest misstep could have catastrophic consequences. One of the primary obstacles is the presence of tidal forces. These forces arise from the difference in gravitational strength between the side of the spacecraft closest to the black hole and the side farthest away. Imagine stretching a rubber band. The closer end gets pulled harder, while the farther end barely moves. In the case of a spacecraft near a black hole, this uneven pull could stretch and compress the vessel, potentially tearing it apart. Engineers would need to design spacecraft with unprecedented structural integrity to withstand these extreme conditions. Beyond tidal forces, spacetime distortion adds another layer of complexity. According to Einstein's theory of general relativity, massive objects like black holes warp the fabric of spacetime. Near the event horizon, this warping becomes so extreme that time itself behaves differently. For an observer far from the black hole, a spacecraft approaching the event horizon would appear to slow down, almost as if frozen in time. This effect, known as gravitational time dilation, poses significant challenges for communication and coordination during such a mission. The intense radiation and debris surrounding a black hole, known as the accretion disk, further complicate navigation. This swirling mass of superheated material emits powerful radiation that could damage sensitive equipment or harm the crew. Navigating through or around this hazardous zone would require advanced shielding and precise trajectory calculations to minimize exposure. Despite these challenges, mastering event horizon navigation could unlock unprecedented opportunities for intergalactic travel. Successfully skirting the edge of a black hole's event horizon could allow spacecraft to harness its immense gravitational energy, propelling them to speeds that would make distant regions of the universe accessible. This technique could serve as a cosmic shortcut, drastically reducing travel times and opening up new frontiers for exploration. As we consider the potential of event horizon navigation, it's clear that this endeavor would require groundbreaking advancements in technology and a deep understanding of the physics governing black holes. The journey to harness these gravitational giants is fraught with risks, but the rewards could redefine humanity's place in the cosmos. With each challenge we overcome, we move one step closer to making the dream of intergalactic travel a reality. Now shifting our gaze to the quantum realm, let's delve into the intriguing concept of space-time foam. At the smallest scales of the universe, space itself is not smooth and continuous, but instead appears as a frothy, ever-churning sea of fluctuations. This phenomenon, known as space-time foam, arises from the unpredictable nature of quantum mechanics, where particles and energy pop in and out of existence in a chaotic dance. Imagine space as a calm ocean. On the surface, everything seems still and predictable, but beneath lies a turbulent world of waves and currents. Space-time foam is akin to the microscopic turbulence beneath the surface, where the fabric of reality is constantly shifting. These fluctuations are so tiny that they're nearly impossible to observe directly, yet they could have profound implications for intergalactic travel. The unpredictable nature of space-time foam poses unique challenges for spacecraft. As a vessel moves through the cosmos, it would encounter these quantum fluctuations, which could cause minute but potentially disruptive effects on navigation and propulsion systems. Engineers would need to account for this quantum turbulence, designing spacecraft that can adapt to the ever-changing conditions of space-time. One of the most fascinating aspects of space-time foam is its connection to the fundamental nature of reality. Some theories suggest that these fluctuations could create tiny wormholes or shortcuts through space, offering potential routes for faster-than-light travel. While this remains speculative, the idea hints at the untapped possibilities of harnessing the quantum realm for intergalactic exploration. Understanding space-time foam also brings us closer to reconciling the worlds of quantum mechanics and general relativity, two of the most successful yet seemingly incompatible theories in physics. By studying how these quantum fluctuations interact with the larger structure of the universe, scientists could unlock new insights into the nature of space, time, and the very fabric of reality. As we consider the impact of space-time foam on intergalactic travel, it's clear that this quantum phenomenon represents both a challenge and an opportunity. While its chaotic nature presents hurdles for spacecraft design, it also holds the potential to revolutionize our understanding of the cosmos and our ability to traverse it. The journey to master these quantum fluctuations is just beginning, but with each discovery, we edge closer to unlocking the secrets of the universe. Now turning to the heart of the matter, let's explore the concept of quantum turbulence within space-time foam. While we've established that space-time foam is a chaotic, ever-changing landscape at the quantum level, the phenomenon of quantum turbulence takes this a step further. Picture this turbulence as eddies and whirlpools in a river, constantly shifting and unpredictable, yet forming patterns that influence the flow around them. In the context of space-time foam, these quantum eddies could have significant implications for intergalactic travel. As a spacecraft ventures through the cosmos, it would encounter these quantum whirlpools, which could introduce minute but potentially disruptive forces. These forces might affect the vessel's trajectory, propulsion, and even the integrity of its systems. For instance, a sudden shift in the quantum fabric could cause slight deviations in navigation, forcing onboard systems to make constant adjustments. Over vast distances, even the smallest fluctuations could compound, leading to significant deviations from the intended path. To address these challenges, engineers would need to develop advanced navigation systems capable of detecting and responding to quantum turbulence in real time. Imagine a spacecraft equipped with quantum sensors, constantly monitoring the fabric of space-time and making adjustments to maintain stability. This would require not only cutting-edge technology, but also a deeper understanding of how quantum turbulence operates on a macroscopic scale. One intriguing possibility is that these quantum fluctuations could be harnessed rather than merely mitigated. Some theorists suggest that by aligning a spacecraft's propulsion system with the natural flow of quantum turbulence, it might be possible to ride the waves of space-time, achieving more efficient travel. While this idea is still in its infancy, it highlights the dual nature of quantum turbulence as both a challenge and a potential tool for innovation. The study of quantum turbulence is not just about overcoming obstacles, it's also about expanding our understanding of the universe. By examining how these fluctuations interact with spacecraft and other objects, scientists could gain new insights into the fundamental nature of space and time. This knowledge could pave the way for breakthroughs in physics, propulsion, and even our ability to explore the cosmos. As we continue to unravel the mysteries of quantum turbulence, one thing is clear: the journey through space-time foam is anything but smooth. Yet, within this chaos lies the potential for discovery, innovation, and a deeper connection to the universe itself. With each step forward, we move closer to turning these quantum curiosities into tools for intergalactic exploration. As the conversation shifts to the realm of hyperdimensional physics, we enter a world where the universe may hold more layers than meets the eye. Hyperdimensional physics suggests that beyond the familiar 3 dimensions of space and 1 of time, there could exist additional dimensions that are hidden from our everyday perception. Imagine these higher dimensions as unseen pathways or shortcuts that could revolutionize how we think about intergalactic travel. At its core, this theory builds on ideas from string theory, which proposes that the fundamental particles of the universe are not just tiny points but one-dimensional strings vibrating in higher dimensional space. While these extra dimensions are thought to be incredibly small and tightly curled up, they could still play a crucial role in shaping the fabric of reality. For intergalactic travel, this opens up fascinating possibilities. If we could access or manipulate these higher dimensions, it might allow us to bypass the vast distances that currently make space travel so daunting. One speculative idea is that these extra dimensions could serve as conduits for faster travel, effectively creating tunnels or bridges between distant points in the universe. Think of it like folding a piece of paper to bring 2 distant points together, except, in this case, the folding would occur in higher dimensional space. While this concept remains theoretical, it's grounded in mathematical models that suggest such pathways could exist. Another angle explores how higher dimensions might influence the behavior of gravity. In some theories, gravity is weaker in our observable universe because it leaks into these extra dimensions. If we could harness or control this phenomenon, it might lead to new propulsion methods that defy our current understanding of physics. For example, a spacecraft designed to interact with higher dimensions could potentially manipulate gravity itself, allowing for unprecedented speeds and maneuverability. Of course, the challenge lies in detecting and accessing these dimensions. Scientists have proposed experiments to search for evidence of higher dimensions, such as observing deviations in gravitational behavior at extremely small scales. While no definitive proof has been found yet, the pursuit of these ideas continues to push the boundaries of our knowledge. As we explore the implications of hyperdimensional physics, one thing becomes clear: the universe may be far more complex and interconnected than we've ever imagined. By unlocking the secrets of these hidden dimensions, we could open the door to a new era of space exploration, where the stars are no longer out of reach but just a fold away. Now, shifting our focus to brain theory, we delve into a concept that redefines our understanding of the universe's structure. Brain theory proposes that our entire universe exists not as an isolated entity, but as a brain or membrane floating within a higher dimensional space. Think of our universe as a single sheet of paper in a vast stack of papers, each representing a different brain in a multidimensional framework. This idea emerges from string theory, which suggests that these brains could be the foundational building blocks of reality, vibrating and interacting in ways that shape the cosmos. One of the most intriguing implications of brain theory for intergalactic travel lies in the possibility of interactions between these membranes. If our universe is one brain among many, what if we could tap into the spaces between them? Some theories suggest that these higher dimensional gaps could act as shortcuts, allowing us to traverse immense distances in ways that defy conventional physics. Imagine slipping from one brain to another, bypassing the limitations of our three-dimensional space entirely. Another fascinating angle is the idea of gravity leaking between brains. In brain theory, gravity is unique in that it can extend beyond our brain into the higher dimensional space, known as the bulk. This could explain why gravity appears weaker compared to other fundamental forces in our universe. If we could harness this phenomenon, it might lead to revolutionary propulsion methods, enabling spacecraft to manipulate gravity in ways that propel them across the cosmos at incredible speeds. The challenge, of course, is detecting and accessing these higher dimensions. Experiments like those searching for gravitational anomalies at microscopic scales aim to uncover evidence of brain theory's validity. While this remains a speculative field, the potential implications are staggering. By understanding how brains interact and how our universe fits into this multidimensional puzzle, we could unlock entirely new ways to explore the stars. As we consider brain theory's possibilities, it becomes clear that our universe may be just one layer in a far more complex reality. The exploration of these hidden dimensions could transform not only our understanding of space and time, but also our ability to travel beyond the confines of our galaxy. Now, turning to the intriguing concept of dark matter engines, we explore a theory that could revolutionize how we approach intergalactic travel. Dark matter, the mysterious substance that makes up about 27% of the universe, does not emit light or energy, making it invisible and incredibly difficult to detect. Yet, its gravitational effects on galaxies and cosmic structures tell us it's there. What if we could use this elusive substance as a power source for our spacecraft? The idea behind dark matter engines hinges on the principle that dark matter interacts with gravity and could potentially be harnessed to propel a vessel. Imagine a spacecraft equipped with technology that collects or manipulates dark matter, converting its gravitational pull into thrust. This could provide an almost limitless energy source, enabling us to travel vast distances without the need for traditional fuel sources. However, the challenges are immense. First, we still don't fully understand the nature of dark matter. While we can observe its effects, we have yet to directly detect or isolate it. This makes developing the technology to harness it a monumental task. Second, even if we could detect dark matter, manipulating it for propulsion would require breakthroughs in physics and engineering that are currently beyond our reach. Despite these obstacles, the potential rewards are staggering. A dark matter engine could provide the energy efficiency and longevity needed for intergalactic voyages, overcoming one of the biggest hurdles in space travel. As research into dark matter continues, this theory serves as a reminder of how much we still have to learn about the universe and the incredible possibilities that lie ahead. As we venture into this uncharted territory, the pursuit of dark matter engines challenges us to think beyond conventional boundaries, pushing the limits of science and imagination. Now, shifting our focus to the enigmatic force known as dark energy, we uncover another layer of the universe's mysteries that could transform intergalactic travel. Dark energy, the invisible force driving the accelerated expansion of the universe, makes up roughly 68% of the cosmos. Unlike dark matter, which pulls objects together through gravity, dark energy pushes them apart, causing galaxies to move away from each other at increasing speeds. But what if we could tap into this vast, unseen power to propel our spacecraft? The concept of harnessing dark energy for propulsion revolves around the idea of capturing or redirecting this outward force. Picture a spacecraft equipped with advanced technology that could channel dark energy, using its repulsive nature to create thrust. This would allow us to travel immense distances without relying on traditional fuel sources, potentially overcoming one of the greatest challenges of space exploration. However, the hurdles are significant. First, our understanding of dark energy is still in its infancy. While we know it exists and affects the universe's expansion, we have yet to determine its exact nature or behavior. Second, even if we could comprehend how dark energy works, developing the technology to harness it would require breakthroughs in physics and engineering that are currently beyond our capabilities. Despite these challenges, the potential applications are extraordinary. A dark energy propulsion system could theoretically enable us to travel faster and farther than ever before, opening up new frontiers in the cosmos. As scientists continue to study this mysterious force, the possibilities for its use in intergalactic travel remain a tantalizing prospect. Exploring dark energy not only deepens our understanding of the universe, but also inspires us to rethink the boundaries of what's possible in space exploration. It's a reminder that the cosmos is full of untapped potential, waiting for us to unlock its secrets. Shifting our gaze to another cosmic marvel, let's explore the intriguing possibility of cosmic strings acting as celestial highways for intergalactic travel. Cosmic strings are hypothetical one-dimensional structures that are thought to have formed in the early universe. These incredibly thin, yet unimaginably dense threads of energy stretch across vast distances, potentially spanning entire galaxies or even the universe itself. The idea of using cosmic strings for travel hinges on their unique properties. Unlike any known material, cosmic strings possess immense gravitational fields due to their extreme density. This could allow spacecraft to ride along their length, harnessing their gravitational pull for propulsion. Imagine a cosmic highway system where these strings serve as natural pathways through the void of space, enabling us to traverse incredible distances in a fraction of the time it would take with conventional methods. However, the physics behind cosmic strings is still largely theoretical. While they are predicted by certain models in quantum physics and string theory, their existence has yet to be confirmed. Detecting these elusive structures would require groundbreaking advancements in observational technology. Even if we could locate them, navigating the intense gravitational forces near cosmic strings would pose significant challenges, requiring advanced shielding and propulsion systems to ensure the safety of travelers. Despite these obstacles, the potential applications of cosmic strings are extraordinary. If harnessed, they could revolutionize our approach to intergalactic travel, offering a shortcut through the cosmos that bypasses the limitations of distance and time. As scientists continue to probe the mysteries of the universe, the concept of cosmic strings remains a fascinating glimpse into the possibilities that await us in the vast expanse of space. This theory not only expands our understanding of the universe's structure, but also ignites our imagination, reminding us that the cosmos is filled with untapped wonders waiting to be explored. Now turning to the fascinating realm of string theory, we uncover a deeper connection to the concept of cosmic strings and their potential role in intergalactic travel. String theory proposes that the fundamental building blocks of the universe are not point-like particles but incredibly tiny, vibrating strings. These strings, existing in multiple dimensions, give rise to all the particles and forces we observe in nature. In this framework, cosmic strings emerge as a natural consequence. They are effectively giant, one-dimensional versions of these fundamental strings, stretching across the universe like cosmic highways. The immense energy and gravitational fields predicted by string theory align perfectly with the properties of cosmic strings, making them a plausible, if not yet proven, feature of our universe. But how does this tie into intergalactic travel? String theory suggests that the behavior of these fundamental strings could influence the stability and functionality of cosmic strings. For instance, the vibrations of these strings determine the properties of particles, including those that might interact with cosmic strings in ways we don't yet fully understand. Imagine a scenario where advanced civilizations could manipulate these vibrations to stabilize or even create artificial cosmic strings, effectively building their own intergalactic transportation networks. Moreover, string theory's multidimensional nature opens up intriguing possibilities. If our universe is just one brain floating in a higher dimensional space, cosmic strings could act as bridges between these dimensions, offering pathways not just across galaxies but potentially between universes. While this remains speculative, it highlights the profound implications of string theory for our understanding of space and travel. As we explore these ideas, it's important to remember that string theory is still a work in progress, with many of its predictions yet to be tested. Yet, its connection to cosmic strings offers a tantalizing glimpse into how the fundamental nature of the universe might one day unlock the secrets of intergalactic travel. This theory reminds us that the cosmos is not only vast but also deeply interconnected, with every discovery bringing us closer to understanding its most profound mysteries. As we venture into the next frontier of intergalactic possibilities, let's shift our focus to the transformative role of nanotechnology in spacecraft design. Imagine a vessel that can heal itself, adapt to unforeseen challenges, and optimize its performance in real time. This is the promise of nanotechnology ships, a concept that could redefine how we approach the vastness of space. Nanotechnology, the science of manipulating matter at an atomic or molecular scale, offers unprecedented capabilities for spacecraft construction. By integrating nanoscale materials and devices, we could create ships with self-repairing hulls that automatically patch up damage from micrometeoroids or radiation. These materials could also adjust their properties in response to environmental changes, such as extreme temperatures or pressure, ensuring the ship remains functional in the harshest conditions. Beyond structural resilience, nanotechnology could revolutionize onboard systems. Nanobots, tiny robots no larger than a cell, could be deployed to maintain and repair critical components like engines, life support systems, and communication arrays. This would reduce the need for human intervention during long voyages, minimizing risks and ensuring the ship operates smoothly across immense distances. However, the potential of nanotechnology ships is not without challenges. One major limitation is the complexity of designing and producing these advanced materials and devices. Current technology is still in its infancy, and scaling up nanotech applications for spacecraft remains a significant hurdle. Additionally, the long-term effects of nanobots in closed environments, such as potential contamination or malfunction, need thorough investigation to ensure safety and reliability. Another consideration is the energy required to power these systems. Nanotechnology ships would demand efficient energy sources to sustain their advanced functions, which could pose a challenge given the constraints of current propulsion technologies. Despite these obstacles, the promise of nanotechnology ships is undeniably exciting. By merging cutting-edge science with innovative engineering, we could create vessels capable of enduring the rigors of intergalactic travel while ensuring the safety and efficiency of their crews. This theory reminds us that the future of space exploration may lie not in building bigger ships, but in making them smarter, more adaptable, and self-sufficient. As we continue to explore these revolutionary ideas, it's clear that the marriage of nanotechnology and space travel could unlock new pathways to the stars. The journey ahead is as much about technological ingenuity as it is about venturing into the unknown, and nanotechnology may well be the key to making that journey possible. Now turning to the fascinating world of nanobots in space, let's explore how these microscopic machines could become the unsung heroes of intergalactic travel. Picture this, a swarm of nanobots, each no larger than a grain of sand, working tirelessly to ensure the spacecraft remains in peak condition, even in the most remote corners of the universe. These tiny marvels could perform tasks ranging from repairing critical systems to constructing new infrastructure, all while supporting the delicate balance of life on board. One of the most remarkable capabilities of nanobots lies in their ability to maintain spacecraft systems autonomously. Imagine a scenario where a vital component of the ship's engine begins to fail. Instead of relying on human intervention, nanobots could swiftly diagnose the issue, locate the problem, and execute precision repairs at the molecular level. This would not only minimize downtime but also reduce the risks associated with manual repairs in the harsh environment of space. Beyond maintenance, nanobots could play a pivotal role in building infrastructure during long journeys. Whether it's assembling new modules for the spacecraft or creating tools and equipment from raw materials found in space, these tiny machines could transform the way we approach resource utilization. For instance, they could harvest asteroids for metals or convert cosmic dust into essential components, ensuring the ship remains self-sufficient across vast distances. Supporting life on board is another critical function nanobots could fulfill. In the confined environment of a spacecraft, maintaining air quality, water purity, and food production is essential. Nanobots could monitor these systems, detect contaminants, and even assist in recycling waste into usable resources. They could also aid in medical emergencies by delivering targeted treatments or repairing cellular damage, ensuring the crew remains healthy throughout the journey. However, integrating nanobots into space travel is not without its challenges. One major concern is the potential for malfunctions or unintended interactions within the closed ecosystem of a spacecraft. Ensuring the reliability and safety of these machines requires rigorous testing and sophisticated control mechanisms. Additionally, the energy demands of nanobots must be addressed, as their continuous operation could strain the ship's power supply. Despite these hurdles, the potential of nanobots in space is immense. By combining advanced robotics with cutting-edge nanotechnology, we could create a new paradigm for intergalactic travel, one where the ship itself becomes a living, self-sustaining entity powered by the tireless efforts of its microscopic crew. This vision reminds us that the future of space exploration lies not just in grand designs, but in the intricate, unseen technologies that make the impossible possible. As we look to the stars, it's clear that nanobots could be the key to overcoming the challenges of long-duration space travel. By harnessing their capabilities, we pave the way for a future where humanity can venture beyond our galaxy with confidence, knowing that these tiny guardians are there to support us every step of the way. As we reach the end of our journey through 30 groundbreaking theories about the universe's first intergalactic travel, it's impossible not to marvel at the sheer creativity and ingenuity behind these ideas. From wormholes bending spacetime to nanobots repairing spacecraft, each theory offers a glimpse into the boundless possibilities of human imagination and scientific exploration. We've explored how advanced civilizations might harness technologies like the Alcubierre Drive, navigate black holes, or even venture into parallel universes. We've pondered the challenges of generation ships, cryogenic sleep, and harnessing dark energy, each concept pushing the boundaries of what we believe is possible. These theories remind us that the quest to explore the cosmos is not just about reaching distant stars, but about redefining our understanding of the universe and our place within it. They inspire us to dream bigger, think deeper, and consider the incredible potential of human innovation. Now it's your turn to join the conversation. Which of these theories do you find most plausible or exciting? Could wormholes become cosmic highways, or will artificial intelligence pilots guide us to the farthest reaches of space? Share your thoughts in the comments below and let's keep the discussion alive. If you've enjoyed this deep dive into the mysteries of intergalactic travel, don't forget to hit the like button, subscribe to our channel, and ring the notification bell so you never miss out on our next adventure into the unknown. The universe is full of wonders waiting to be discovered, and we're just getting started. Until next time, keep looking up and dreaming.